Welcome to Cosmic Whispers, where cosmic mysteries come alive. Your journey beyond the stars begins now. Deep within the heart of every tree, locked in the very structure of cellulose and lignin, lies one of Earth's most precious resources, carbon. This element, fundamental to all life as we know it, doesn't simply sit static in our forests. Instead, it flows through an intricate web that connects every living thing on our planet, from the smallest soil microbe to the vast atmospheric ocean above our heads. When lightning strikes a drought-stricken forest, or when human activity ignites vegetation, something profound happens to this carbon web. In seconds, carbon that trees have carefully captured from the atmosphere over decades gets released back into the sky as smoke and gases. But this isn't just a simple give and take. Forest fires represent one of the most dramatic and consequential disruptions to Earth's carbon cycle, sending ripples through interconnected systems that span continents and oceans. Every year, fires consume approximately 400 million hectares of land worldwide. That's an area larger than the entire European Union going up in flames annually. These fires release between 2 and 4 billion tons of carbon into the atmosphere, representing roughly 10 to 20% of global carbon dioxide emissions. To put this in perspective, that's equivalent to the annual emissions of the entire United States. But here's where the story becomes truly fascinating. Fires aren't simply carbon destroyers. They're carbon transformers, reshaping how this vital element moves through Earth's systems in ways that scientists are only beginning to fully understand. Some fires actually enhance long-term carbon storage, while others trigger cascading effects that amplify climate change for decades. Every great journey starts with a few brave explorers. Right now, Cosmic Whispers is just beginning, and your support means everything. If you enjoy unraveling the mysteries of the universe, hit subscribe. It's free, and it helps us grow this community together. The relationship between fire and carbon operates on multiple timescales simultaneously. In the immediate aftermath of a fire, the chemistry is straightforward. Organic matter burns, releasing stored carbon as carbon dioxide and other compounds. But zoom out to decades or centuries, and the picture becomes remarkably complex. Fire-cleared areas might regrow more vigorously, potentially sequestering more carbon than before. Alternatively, repeated fires might convert forests into grasslands, permanently altering regional carbon storage capacity. Modern satellite observations reveal that fire patterns are shifting dramatically. The boreal forests of Canada and Siberia, which contain some of Earth's largest carbon reserves, are burning more frequently and intensely than at any point in recorded history. These northern fires are particularly significant because they're releasing carbon from permafrost and peat soils that have been locked away for millennia. Meanwhile, tropical fires in the Amazon and Southeast Asia are destroying some of the planet's most carbon-rich ecosystems, while also disrupting rainfall patterns that affect carbon cycling across entire continents. Each of these fire regimes operates differently, releasing carbon through distinct mechanisms and timescales. Understanding how forest fires affect the global carbon web requires us to think like detectives, following carbon molecules through their journey from living wood to atmospheric gases, then tracking their ultimate fate as they influence everything from local weather patterns to global climate systems. This investigation will take us from the molecular level of combustion chemistry to the planetary scale of Earth system interactions, revealing how fire serves as both creator and destroyer in the grand story of carbon on our planet. Fire has been reshaping Earth's carbon landscape for over 400 million years, long before humans ever walked the planet. This ancient relationship between combustion and carbon cycling tells a story of co-evolution, where life itself learned to harness and adapt to fire's transformative power. During the Devonian period, as the first forests spread across the continents, atmospheric oxygen levels rose dramatically. This oxygen-rich environment made fires more frequent and intense, creating the first major disruptions to terrestrial carbon storage. Fossil evidence shows that these early fires didn't just consume vegetation randomly. They began establishing patterns that would persist for millions of years. Ancient charcoal deposits reveal that fire frequency varied dramatically with climate cycles. During ice ages, When atmospheric carbon dioxide levels dropped and climates became drier, fires actually increased in some regions, creating a fascinating feedback loop. As fires released stored carbon, they contributed to atmospheric warming that eventually helped end ice ages. This demonstrates that fire has always been both a responder to and driver of climate change. The evolution of fire-adapted ecosystems represents one of nature's most remarkable innovations in carbon management. Pine forests developed thick bark and high crowns to survive fires, while also producing resin-rich tissues that actually encourage burning. This seems counterintuitive until we understand the carbon strategy. These trees use fire to clear competitors and release nutrients, then rapidly regrow to capture carbon more efficiently than their predecessors. Savanna ecosystems took fire adaptation even further, developing underground carbon storage systems that fires cannot reach. Grasses store up to 70% of their carbon in extensive root networks below ground. When surface fires sweep through these landscapes, they consume only the above-ground biomass while leaving the vast underground carbon reservoirs intact. This strategy allows savannas to maintain stable carbon storage despite frequent burning. Indigenous peoples around the world developed sophisticated fire management practices that worked with these natural carbon cycles. In Australia, Aboriginal communities used controlled burning to maintain landscapes for over 60,000 years. Their fire regimes typically released smaller amounts of carbon more frequently, preventing the accumulation of fuel that leads to catastrophic fires. These practices created a mosaic of burned and unburned areas that maximized overall carbon storage while maintaining ecosystem health. Similarly, Native American communities in North America used fire to manage forests and grasslands, creating park-like woodlands with widely spaced trees and carbon-rich soils. These managed landscapes often stored more carbon than densely packed forests because the combination of trees and fire-maintained grasslands created optimal conditions for soil carbon accumulation. The pre-industrial global fire regime was remarkably stable, with natural fires following predictable patterns linked to seasonal rainfall, lightning frequency, and vegetation growth cycles. Climate reconstructions suggest that global fire carbon emissions varied by only about 20% from year to year, despite regional variations caused by events like volcanic eruptions or unusual weather patterns. This stability began changing dramatically with European colonization and the Industrial Revolution. Fire suppression policies, introduced with good intentions to protect human settlements and valuable timber, disrupted carbon cycles that had been stable for millennia. Without regular low-intensity fires to clear accumulated vegetation, forests began storing unnaturally high fuel loads. Simultaneously, human activities began altering atmospheric chemistry in ways that affected fire behavior. Rising carbon dioxide levels made plants grow faster and accumulate more biomass, while nitrogen pollution from agriculture and industry changed plant chemistry, making vegetation more flammable. These changes created conditions for the megafires we see today. Understanding this deep history reveals that fire's role in carbon cycling isn't inherently problematic. For millions of years, fire helped maintain stable carbon reservoirs while supporting biodiversity and ecosystem health. The challenge we face today isn't fire itself, but rather the disruption of ancient fire-carbon relationships by rapid human-induced changes to both climate and land use. This historical perspective provides crucial context for understanding why modern fires behave so differently and release carbon in ways that amplify rather than stabilize climate systems. When a forest fire ignites, it triggers one of nature's most complex chemical transformations. Understanding exactly how carbon moves from living wood to atmospheric gases requires diving deep into the molecular machinery of combustion, where temperatures, oxygen availability, and fuel composition determine not just how much carbon gets released, but in what forms. Trees store carbon in multiple ways, each responding differently to fire. The most obvious reservoir is cellulose, the structural component that gives wood its strength. Cellulose molecules are long chains of sugar units, each containing 6 carbon atoms. When temperatures reach approximately 300 degrees Celsius, cellulose begins breaking down through a process called pyrolysis, splitting into smaller molecules before combustion even begins. Lignin, the polymer that makes wood hard and gives trees their brown color, presents a different challenge for fire. This complex molecule contains roughly 60% carbon by weight and requires higher temperatures to decompose completely. During incomplete combustion, lignin often transforms into charcoal rather than burning completely, creating a stable form of carbon that can persist in soils for centuries. The combustion process itself occurs in distinct phases, each releasing carbon differently. The initial heating phase drives off moisture and volatile compounds, creating the visible smoke that contains carbon monoxide, methane, and hundreds of other carbon-containing molecules. As temperatures climb above 500 degrees Celsius, the main combustion phase begins, where most carbon gets oxidized to carbon dioxide. But fire behavior varies dramatically with fuel moisture, wind speed, and oxygen availability. In well-ventilated fires with plenty of oxygen, combustion efficiency can exceed 90%, meaning most carbon gets converted to carbon dioxide. However, in oxygen-limited conditions, such as the interior of dense fuel beds or during smoldering, phases combustion efficiency drops to as low as 60%. The remaining carbon gets released as partially oxidized compounds or remains as charcoal. Fire temperature profiles reveal why carbon release isn't uniform across a burning forest. Crown fires burning in treetops with abundant oxygen and dry fuel can reach temperatures of 1,000 degrees Celsius or higher. At these temperatures, even the most resistant carbon compounds get fully oxidized. Ground fires burning in soil, organic matter, and root systems typically reach only 200 to 400 degrees Celsius, creating conditions favoring char formation over complete combustion. The timing of carbon release adds another layer of complexity. Fast-moving fires release most of their carbon within hours, creating intense but brief spikes in local atmospheric carbon concentrations. Slow-burning fires, particularly those burning in organic soils and peat, can release carbon continuously for weeks or months. Some deep peat fires burn underground for entire seasons, slowly releasing carbon that accumulated over thousands of years. Soil carbon presents the most variable response to fire. Surface organic layers, consisting of recently fallen leaves and branches, typically burn completely at relatively low temperatures. But deeper soil carbon, protected by moisture and mineral layers, might require direct flame contact to ignite. When deep organic soils do burn, they release disproportionately large amounts of carbon because these layers represent decades or centuries of accumulated organic matter. The chemical composition of fire emissions varies with burn temperature and fuel type. High-temperature fires produce mainly carbon dioxide and water vapor, with smaller amounts of carbon monoxide and nitrogen oxides. Lower-temperature fires create a complex mixture, including methane, formaldehyde, acetaldehyde, and hundreds of other organic compounds. Many of these compounds continue reacting in the atmosphere, eventually converting to carbon dioxide over timescales ranging from hours to years. Smoldering combustion, which occurs when fires burn with limited oxygen, deserves special attention because it can release up to 10 times more carbon monoxide and particulate carbon than flaming combustion. This process often dominates the later stages of fires and can continue long after visible flames disappear. Smoldering fires in organic soils are particularly significant because they can consume entire layers of accumulated carbon that represent centuries of ecosystem development. Recent research has revealed that fire's carbon chemistry extends far beyond simple combustion. High-temperature fires create conditions for forming complex carbon structures, including graphite-like materials and carbon nanoparticles. These materials have different atmospheric lifetimes and climate effects than simple carbon dioxide, adding nuance to our understanding of fire's contribution to climate change. While carbon dioxide captures most attention in discussions of fire emissions, the complete picture reveals a complex cocktail of compounds that affect Earth's climate in diverse and sometimes surprising ways. Understanding these additional emissions is crucial because they can have climate impacts many times greater than carbon dioxide alone, operating through mechanisms that extend far beyond simple greenhouse warming. Methane represents one of the most significant non-carbon dioxide emissions from fires. This molecule, containing one carbon atom surrounded by 4 hydrogen atoms, has a global warming potential approximately 28 times greater than carbon dioxide over a century timescale. Fires produce methane, primarily during smoldering phases when oxygen is limited, with tropical peat fires being particularly prolific methane sources. The amount of methane released varies dramatically with fire conditions. Flaming combustion typically produces methane at rates of 0.5 to 2 grams per kilogram of fuel burned. However, smoldering fires can produce 10 to 50 grams per kilogram, representing a 25-fold increase. Given that smoldering can dominate the total burn time for many fires, methane emissions often exceed what simple flaming models predict. Nitrous oxide, another potent greenhouse gas, forms when fires burn nitrogen-rich vegetation or soils. This compound has a warming potential nearly 300 times greater than carbon dioxide and remains in the atmosphere for over a century. Fires in agricultural areas or forests with nitrogen-fixing plants produce particularly high nitrous oxide emissions, sometimes representing up to 5% of total greenhouse gas impact from these fires. Black carbon, consisting of tiny soot particles, creates climate effects that operate through entirely different mechanisms than greenhouse gases. These particles absorb sunlight directly, warming the atmosphere where they're suspended. When black carbon lands on snow or ice, it reduces surface reflectivity, accelerating melting. Fires produce black carbon primarily during flaming combustion of woody fuels, with emission rates varying from 0.2 to 2.0 grams per kilogram of fuel burned. The climate impact of black carbon depends heavily on where it ends up. Black carbon deposited on Arctic snow and ice has warming effects up to 1,000 times greater per gram than the same particles suspended in tropical atmospheres. This geographic sensitivity means that fires in boreal regions, or those that transport emissions toward polar regions, have disproportionately large climate impacts. Organic carbon particles present the opposite effect, reflecting sunlight and creating cooling influences. Fires typically produce 3 to 10 times more organic carbon particles than black carbon, but the balance between these opposing effects varies with fire temperature, fuel type, and atmospheric conditions. High-temperature fires favor black carbon production, while smoldering fires produce more organic carbon particles. Fire-produced aerosols extend far beyond simple carbon particles. Fires release potassium, chlorine, sulfur, and other elements that form particles affecting both climate and air quality. These particles serve as condensation nuclei for cloud formation, potentially altering precipitation patterns hundreds of miles from fire sources. Some studies suggest that fire aerosols can suppress rainfall by creating too many small cloud droplets, while others indicate enhanced precipitation under certain conditions. The atmospheric chemistry of fire emissions continues evolving long after flames are extinguished. Volatile organic compounds released during burning react with sunlight and other atmospheric constituents to form secondary organic aerosols. These reactions can continue for days, gradually converting gas phase emissions into particles that affect climate and air quality in ways quite different from primary fire emissions. Fire emissions also include trace gases that, while present in small quantities, can have outsized atmospheric effects. Hydrogen cyanide, formaldehyde, and acetaldehyde affect atmospheric chemistry in ways that influence the formation and destruction of ozone, methane, and other climate-relevant compounds. These interactions create feedback loops where fire emissions indirectly affect the atmospheric lifetime of greenhouse gases. Recent advances in atmospheric chemistry modeling reveal that fire emissions can influence climate through complex interactions with natural atmospheric processes. For example, fire-produced nitrogen oxides can enhance methane destruction in some atmospheric regions while promoting its formation in others. Similarly, fire aerosols can either enhance or suppress the formation of natural cloud condensation, nuclei depending on background atmospheric conditions. Understanding these diverse emission pathways is crucial for accurately assessing fire's climate impact. While carbon dioxide typically represents 60 to 80% of the immediate greenhouse warming from fires, The combined effect of all other compounds can equal or exceed carbon dioxide's impact when their various mechanisms and timescales are fully considered. This complexity explains why simple carbon accounting often underestimates fire's true climate significance. The carbon released by forest fires doesn't simply vanish into the atmosphere and disappear. Instead, it triggers cascading effects that ripple through interconnected Earth systems, altering everything from local soil chemistry to global ocean circulation patterns. Understanding these ripple effects reveals how fire's influence on carbon cycling extends far beyond the immediate release of emissions. Soil systems bear the most immediate and long-lasting impacts from fire's carbon disruption. When fires consume surface organic matter, they eliminate the primary source of new soil carbon inputs. This loss might seem temporary, but its effects compound over time. Healthy forest soils typically receive 2 to 5 tons of carbon per hectare annually, from fallen leaves, branches, and root turnover. After severe fires, this input can drop to near zero for several years. The physical properties of post-fire soils create additional challenges for carbon recovery. High-temperature fires can make soil surfaces water-repellent, a condition called hydrophobicity that persists for months or years. This water repellency increases erosion rates, physically removing soil carbon that took decades to accumulate. Studies in fire-prone regions show that severe fires can trigger soil carbon losses of 20 to 50% within the first 5 years after burning. Fire-induced changes to soil temperature and moisture regimes further accelerate carbon loss. Through enhanced microbial activity, darker exposed soil surfaces absorb more heat, while reduced vegetation cover eliminates cooling shade. Soil temperatures in burned areas can average 3 to 5 degrees Celsius higher than in unburned forests, creating conditions that favor rapid decomposition of remaining soil organic matter. The disruption to mycorrhizal networks represents one of fire's most underappreciated impacts on carbon cycling. These fungal networks, sometimes called the wood wide web, connect tree roots across entire forests and play crucial roles in carbon storage and transfer. Fire destroys these networks, severing connections that took decades to establish. Rebuilding. Mycorrhizal networks requires 5 to 15 years, during which forest carbon storage capacity remains significantly reduced. Hydrological changes triggered by fire create feedback loops that affect carbon cycling across entire watersheds. Fire-damaged forests lose their ability to regulate water flow, leading to increased flooding during storms and extended droughts during dry periods. These extreme hydrological conditions stress surviving vegetation and slow forest recovery, prolonging the period of reduced carbon sequestration. Fire's impact on regional climate patterns extends the carbon effects even further. Large fires can alter local temperature and precipitation patterns for years after the flames are extinguished. Reduced forest cover increases surface temperatures and decreases humidity, creating conditions less favorable for forest regrowth. Some studies suggest that extensive fires can shift regional climates permanently, converting forested areas to grasslands or shrublands with fundamentally different carbon storage capacities. The atmospheric transport of fire emissions creates connections between local fires and distant ecosystems. Nutrients from fire smoke can fertilize vegetation thousands of miles away, while fire-produced aerosols can suppress rainfall in regions far from the burn sites. Amazon fires, for example, transport nutrients that fertilize Atlantic Ocean phytoplankton, while also reducing rainfall across the southeastern United States. Ocean carbon cycling responds to fire emissions through multiple pathways. Fire-produced carbon dioxide dissolves directly into ocean waters, contributing to ocean acidification. Meanwhile, fire-generated iron and other nutrients can stimulate phytoplankton growth in nutrient-limited ocean regions, potentially enhancing oceanic carbon sequestration. However, fire aerosols can also reduce the amount of sunlight reaching ocean surfaces, decreasing photosynthesis and carbon uptake by marine organisms. The timing of fire impacts creates complex temporal patterns in carbon cycling. Immediate post-fire. Carbon losses are often followed by periods of enhanced carbon uptake as vegetation regrows. However, The magnitude and duration of this recovery phase depend on fire severity, climate conditions, and the availability of seed sources. Some ecosystems show net carbon gains within 5 to 10 years after fire, while others remain carbon sources for decades. Fire frequency adds another layer of complexity to these ripple effects. Single fires, even severe ones, often lead to eventual carbon recovery. However, repeated fires can create permanent shifts in ecosystem carbon storage. When fires return before forests fully recover, they can convert carbon-rich forests into carbon-poor shrublands or grasslands, fundamentally altering regional carbon balances. Climate change amplifies many of these ripple effects by creating conditions that favor more frequent and severe fires. Warmer temperatures extend fire seasons, while altered precipitation patterns create longer drought periods. These changes are pushing some ecosystems beyond their natural fire adaptation limits, potentially creating permanent shifts in carbon storage patterns that compound global warming trends. Understanding these interconnected effects reveals that fire's impact on the global carbon web operates on multiple scales simultaneously, from local soil processes to global atmospheric circulation patterns, creating changes that persist long after the last ember cools. Human influence has fundamentally transformed the relationship between fire and carbon cycling, creating fire regimes that differ dramatically from natural patterns developed over millions of years. These changes operate through multiple pathways, from direct human ignition sources to subtle alterations in atmospheric chemistry that affect fire behavior in ways only recently understood by scientists. Fire suppression policies, implemented throughout much of the 20th century, created one of the most significant disruptions to natural carbon cycling. Well-intentioned efforts to protect lives and property led to the systematic exclusion of fire from ecosystems that had evolved with regular burning. In fire-adapted forests of Western North America, fire intervals increased from historical averages of 5 to 20 years to current intervals often exceeding 50 to 100 years. This suppression allowed unprecedented fuel accumulation, fundamentally altering how carbon gets released during fires. Historical fires typically consumed 2 to 10 tons of fuel per hectare, releasing carbon gradually through low-intensity burning. Modern fires in suppression-affected forests often encounter fuel loads of 50 to 100 tons per hectare, creating conditions for extreme fire behavior that releases decades of accumulated carbon in single events. The Yellowstone fires of 1988 provided a dramatic illustration of suppression's carbon consequences. These fires burned over 300,000 hectares and released an estimated 8 million tons of carbon in just a few months, equivalent to the annual carbon sequestration of healthy forests covering over 1 million hectares. Similar patterns have repeated across fire-suppressed landscapes worldwide, creating massive carbon pulses that would never have occurred under natural fire regimes. Climate change compounds fire suppression effects through multiple mechanisms that amplify carbon release. Rising temperatures extend fire seasons by up to 75 days in some regions, while earlier snowmelt and increased evaporation create longer drought periods. These changes push vegetation to moisture levels that historically occurred only during extreme weather events, making catastrophic fires more frequent and intense. The feedback loops between climate change and fire create accelerating carbon releases. As fires release more carbon, atmospheric warming increases, creating conditions for even more severe fires. This positive feedback loop is particularly pronounced in boreal regions, where warming temperatures are causing fires to burn deeper into organic soils and permafrost that have stored carbon for millennia. Recent megafires demonstrate the scale of modern carbon disruption. The 2020 Australian bushfires released an estimated 700 million tons of carbon dioxide, more than Australia's total annual fossil fuel emissions. The 2018 Camp Fire in California released approximately 2 million tons of carbon in just 2 weeks. These single events can overwhelm decades of carbon sequestration efforts and forest management programs. Human land use changes create additional pathways for fire carbon disruption. Forest fragmentation creates edge effects that make remaining forests more susceptible to fire, while agricultural expansion often eliminates natural fire breaks. Urban expansion into fire-prone areas, known as the wildland-urban interface, creates pressure for aggressive fire suppression that further disrupts natural fire cycles. The introduction of non-native species has altered fire behavior in subtle but significant ways. Invasive grasses in many regions cure faster and burn more readily than native vegetation, extending fire seasons and creating conditions for fires to spread into previously fire-resistant ecosystems. These invasions can permanently alter carbon storage capacity by preventing the re-establishment of native trees and shrubs. Air pollution from industrial sources affects fire behavior through changes in atmospheric chemistry and plant physiology. Nitrogen deposition from fossil fuel burning fertilizes forest growth, increasing fuel accumulation rates. Simultaneously, ozone pollution stresses trees, making them more susceptible to fire and slower to recover after burning. These effects interact in complex ways that scientists are still working to understand. Modern fire management faces the challenge of restoring natural fire patterns while protecting human values. Prescribed burning programs attempt to reintroduce fire under controlled conditions, reducing fuel loads and restoring natural carbon cycling patterns. However, the scale of these programs remains far below what would be needed to fully restore historical fire regimes. The window for restoring natural fire-carbon relationships may be closing as climate change accelerates. Some ecosystems may have already crossed thresholds where historical fire patterns are no longer viable under current climate conditions. This reality forces managers to consider novel approaches that work with changing conditions rather than attempting to restore historical patterns. International cooperation on fire management is becoming increasingly important as fire effects transcend national boundaries. Smoke from Canadian fires affects air quality across the United States, while Indonesian peat fires influence weather patterns throughout Southeast Asia. These transboundary effects require coordinated responses that consider fire's role in global carbon cycling rather than just local impacts. The challenge of understanding and managing fire's impact on global carbon cycling has driven remarkable advances in monitoring technology, from space-based satellites that track individual fire plumes to ground-based sensors that measure soil carbon changes with unprecedented precision. These tools are revealing patterns in fire-carbon interactions that were invisible just a decade ago. Satellite monitoring has revolutionized our ability to track fire emissions in real time. NASA's MODIS instruments, aboard the Terra and Aqua, satellites detect active fires worldwide every 12 hours, providing data that enables scientists to calculate carbon emissions as fires burn. The European Space Agency's Sentinel satellites add even higher resolution observations, capable of detecting fires as small as 1 hectare and tracking their progression hour by hour. Advanced atmospheric chemistry models now integrate satellite fire data with weather patterns to predict how fire emissions will move through the atmosphere. The Global Fire Emissions Database, updated monthly, combines satellite observations with ground-based measurements to provide the most comprehensive picture ever assembled of global fire carbon emissions. This database reveals that fire emissions vary by up to 300% from year to year, with drought years producing dramatically more emissions than wet years. Ground-based monitoring networks provide crucial validation for satellite observations while measuring carbon cycling processes invisible from space. The FluxNet network operates over 800 towers worldwide that continuously measure carbon dioxide exchange between ecosystems and the atmosphere. These towers reveal that fire effects on carbon cycling can persist for decades, with some sites showing altered carbon balances 20 years after burning. Innovative carbon accounting approaches are emerging to better quantify fire's climate impact. The Global Carbon Project now includes detailed fire emission estimates in annual carbon budget assessments, revealing that fires contribute approximately 2 billion tons of carbon dioxide annually to the atmosphere. However, accounting for fire's full climate impact requires considering not just immediate emissions but also long-term changes in ecosystem carbon storage capacity. The development of carbon offset protocols for fire management represents a Significant advance in applying market mechanisms to carbon cycling problems. Programs in California, Australia, and other regions now provide financial incentives for prescribed burning and other fire management activities that reduce net carbon emissions. These programs must address complex questions about permanence, additionality, and leakage that are particularly challenging in fire-prone ecosystems. Artificial intelligence and machine learning are transforming fire prediction and management capabilities. Google's AI fire prediction system, developed in partnership with NASA, can forecast fire behavior up to 6 hours in advance, with accuracy exceeding 80%. These systems integrate weather data, fuel moisture measurements, topographic information, and satellite observations to provide fire managers with unprecedented situational awareness. Forest management strategies are evolving to explicitly consider carbon storage, alongside traditional objectives like timber production and biodiversity conservation. The concept of climate-smart forestry emphasizes practices that maintain or enhance forest carbon storage while building resilience to future fire regimes. This approach recognizes that optimal management strategies may differ significantly from historical practices as climate conditions change. Prescribed burning programs are expanding rapidly as managers recognize their importance for both carbon management and fire risk reduction. The southeastern United States now burns over 1 million hectares annually through prescribed fire programs, maintaining fire-adapted ecosystems while reducing the risk of catastrophic wildfires. These programs demonstrate that proactive fire management can maintain stable carbon cycling even in changing climate conditions. International cooperation on fire and carbon management is advancing through initiatives like the Global Fire Monitoring Center and the International Crown Fire Modeling Experiment. These programs facilitate data sharing and coordinate research across national boundaries, recognizing that fire effects on carbon cycling operate at global scales that transcend political boundaries. Climate change adaptation strategies increasingly recognize fire as both a threat and a tool for carbon management. The Paris Agreement's implementation guidelines now include specific provisions for accounting fire emissions and forest carbon storage, while the IPCC's latest assessment reports dedicate entire chapters to fire-climate interactions. Looking toward the future, emerging technologies promise even greater capabilities for monitoring and managing fire-carbon interactions. Hyperspectral satellite sensors will enable detection of fire effects on vegetation health and carbon storage at unprecedented scales. Drone-based sensors are already providing detailed mapping of post-fire carbon recovery, while advances in soil carbon measurement techniques are revealing the underground dimension of fire effects. The integration of social and ecological considerations in fire management represents perhaps the greatest challenge and opportunity ahead. Successful fire carbon management requires balancing immediate human safety concerns with long-term carbon cycling objectives, often in landscapes where millions of people live in fire-prone areas. Meeting this challenge will require innovative approaches that protect both human communities and the global carbon systems that regulate Earth's climate. The future of fire's role in global carbon cycling depends on decisions being made today about forest management, urban planning, and climate policy. With the right combination of technology, science, and social commitment, it may be possible to restore fire-carbon relationships that support both ecosystem health and climate stability, ensuring that fire serves as nature's renewal agent rather than a driver of catastrophic change.